We're continuing with Chapter 7, which is on techniques of integration. In this video, we're going to go through Section 7.3, which is on trigonometric substitution. And so I know personally this was a topic in calculus that I found very confusing, but let's walk through this carefully, and I think you'll see it's not so bad. And so the first reason this might be confusing for you is that, so in the previous section, the previous section was titled Trigonometric Integrals. And then now here we're talking about trigonometric substitution. And so with trigonometric substitution, the actual integral that you're trying to solve, in most cases, it doesn't contain a trigonometric function. The integrand doesn't contain a trigonometric function. Okay, so then why is it called trigonometric substitution? It's called this because we're going to make a substitution to solve the integral, and that substitution is going to involve a trigonometric function. Okay, so it says, in finding the area of a circle or an ellipse, an integral of the form, so the integral of the square root of a squared minus x squared dx arises where a is greater than 0. Okay, so if you're finding the area of a circle or an ellipse, you end up with an integral like this, right? Think about the equation of a circle. X squared plus y squared is equal to r squared. Well, in that case, the circle is centered at the origin, but that's the general form. So you solve for y, and you get that y is equal to plus or minus the square root of a squared minus x squared. But you only can potentially have to integrate the positive function because it's symmetrical. So you get an integral that's of a form like this. All right. Now, if this integral had an x term included, then we could make a u substitution, because if we said u is equal to a squared minus x squared, then du is equal to minus 2x dx, and that allows us to substitute here, and it works. But without that x term, this integral is more difficult. We can't just do a normal u substitution. Okay, but to solve this, we can do another kind of substitution where we say that x is equal to a sine theta. And this is where, so you see the substitution is going to involve a trigonometric function. That's why it's called trig substitution. The original integral doesn't have a trig function, but the substitution is going to involve a trig function. And so what happens is, if we come here, if we say x is equal to a sine theta, you get a squared minus a squared sine squared theta. Factor out an a squared times 1 minus sine squared theta. 1 minus sine squared theta is cosine squared theta. And this simplifies to a times the absolute value of cosine theta. And they put absolute value because this is a principal root symbol, right? For some values of theta, cosine theta is negative, but a negative value wouldn't make sense in regards to this principal root symbol. So you put the absolute value. All right, so that's the idea. By making this substitution, we've simplified this, the square root of a squared minus x squared, to something that we can integrate. Okay, and so it points out here that this technique it's the substitution rule, but in reverse. And what they mean by that is, with the substitution rule, we defined the variable that we were substituting with as a function of the original variable in the integral, right? So if you had something like this, then we say we're substituting in u, and the u is a function of the variable within the integral. However, what we just did here was, so, okay, here's the integral. So we're going to replace x with theta, but we don't say theta is equal to some function of x. The theta is, instead, the theta is a function of the variable that's already in the integrand, right? X is equal to a sine theta. You see the difference? And so what they do is they got dx d theta is equal to a cosine theta. So dx is equal to a cosine theta d theta. And then that's how you get rid of the dx. And then you just replace x with a sine theta. And now you've replaced the x with the full integral as a function of theta. Okay, and so another way to show that it's the substitution rule in reverse, if you look here, the substitution rule, you start with, you're defining the original integral as like f of g of t times g prime of t dt. And then you make the substitution and it condenses it down to something simpler, right? However, here we're going in reverse. We're creating an integral that we end up with more terms. So we have an f of x dx, and then we actually end up with the dx is replaced by like a cosine theta d theta, right? We actually end up with the g prime of t dt. But the idea is, though, this f of g of t is something we can work with. That's why we're doing it. The f of x, which has like a square root that we can't work with, ends up becoming this f of g of t that is something we can work with. Okay? This kind of substitution is called inverse substitution. We can make the inverse substitution provided that it defines a one-to-one function. Okay? So to do this inverse substitution, we need to have a one-to-one function, which means that, so you start with x is equal to some function of theta, and then you can equivalently write theta as a function of x with no issue. And so we can do this by restricting theta to lie, the domain of theta, between minus pi over 2 to pi over 2. Kind of like with inverse trig functions. That's how we define inverse trig functions, by restricting the domain of the trig function, the original trig function. In each case, the restriction on theta is imposed to ensure that the function that defines the substitution is one-to-one. Okay, so now it gives a really nice table. You might be wondering, well, how do I know when I can apply this, a trig substitution? Well, it gives a table here showing 3 scenarios where you can apply a trig substitution, and these are the only 3 scenarios. And so that's something else that I found confusing when learning this. You kind of wonder, well, is it kind of like integration by parts where you can apply trig substitution in just any situation? Same thing with like a U substitution, right? You can just apply it whenever. You just have to recognize when it will work. No, trig substitution is not as general, not even close to as general as U substitution or integration by parts. It's specific cases where, so here it gives, if you have the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared. And it's not like you just have to be taking the, so these are the only 3 cases that involve trig substitution. This is it. So if you don't have an integral that's involving something like this, then you're not going to be using a trig substitution. Now, you do have to have a little bit of flexibility in the sense that it's not like this is just applied for the integral, the indefinite integral of a squared minus x squared dx, and that's it. It's not like this is the only integral that you can use this trig substitution for. But the integral is going to contain this, maybe in the denominator, in the numerator, or just in some way it's going to contain this. Okay, now you might have an integral, if we come here, you might have an integral like this, and you don't need to use a trig substitution. You could just use a U substitution. But it could be that you have a term like this, and it's in the function somewhere, and you might say to yourself, well, okay, well, let me try a trig substitution here, and that might work. And same thing with these two. Now, another thing is you might be able to use a trig substitution for a slight offshoot of these. So we're going to see a couple of problems where, it has like an a squared minus x squared, but it's not under a square root. It's like a squared minus x squared squared. Okay, but the idea is you can still consider a trig substitution. And why is that? Because if we come here, anytime you have like something squared minus the variable squared, or something like an a squared minus x squared, or x squared minus a squared, if you make the trig substitution, you know you're going to greatly simplify this a squared minus x squared to just like a simple trig function. So it's really any, it doesn't have to be a square root, it's any situation. It works really great for the square root because it eliminates the square root, right? But even if this was this squared, a squared minus x squared squared, a to the fourth cosine theta to the fourth is still a lot cleaner than a squared minus x squared to the squared, right? So you might want to use the trig substitution there. Okay, but in general, these are the only three cases where you use trig substitution, where these expressions are involved in the function, the integrand somehow, or potentially slight offshoots from these. It's really more about taking the vast majority of the problems we're going to work, it's going to have one of these three expressions involved in the integrand. It's somewhere included in the integrand function. That's the vast majority of the problems we're going to work are going to be like that. But potentially there could be slight offshoots in the sense that it might not be a square root, but it's always going to involve like a squared minus x squared, a squared plus x squared minus a squared, because that's what the trig substitution is doing. It's greatly simplifying that x squared minus a squared plus x squared. That's the idea. Okay. And so to make this work, it gives you, okay, so if you come across an expression, one of these three expressions, all right? So a squared minus x squared, the square root of a squared minus x squared, if you substitute x is equal to a sine theta, and you're restricting, to make sure it's 1-to-1, you're restricting the theta to this range, then in combination with this identity, you'll greatly simplify this. Okay, for a squared plus x squared, if you do x is equal to a tangent theta with the same domain restriction and you use this trig identity, then it'll work out to where you'll greatly simplify this. And then for x squared minus a squared, if you do x is equal to a secant theta with this domain restriction to make sure it's 1-to-1 and this trig identity, you'll greatly simplify this. All right, let's take a look at some examples. So we want to evaluate this integral here. And so, you think, well, maybe a u substitution. But if we said, u is equal to 9 minus x squared, then du is minus 2x dx. That doesn't work. But you see this square root of 9 minus x squared. You can write this as a difference of two squares. And, again, it's really the most important piece is you have the 9 minus x squared. But, again, the majority of the time it's going to be the square root of something like 9 minus x squared. But technically, it doesn't have to be the square root. If you just see if you saw 9 minus x squared, you know that you could make a trig substitution and turn this into like just a constant times a trig function. Okay, but again, the vast majority of the examples that we're going to work, it's going to be the square root of something squared minus something squared, that you can write it in that form. Okay, so if we come to the table, we've got 3 squared minus x squared. So we're going to say x is equal to 3 sine theta, and then they want to specify the domain restriction. And so, dx d theta is equal to 3 cosine theta. So dx is equal to 3 cosine theta d theta. You plug it in, and this is 3. This simplifies, this square root of 9 minus x squared simplifies to 3 absolute value cosine theta, but because of the domain restriction, minus pi over 2 to pi over 2, if you think about the unit circle, cosine theta is always positive in this region. So this is just equal to 3 cosine theta. Okay, and so this is the square root of 9 minus x squared is 3 cosine theta, and then x squared, since x is equal to 3 sine theta, this is 9 sine squared theta. And the dx is 3 cosine theta d theta. And then, so this simplifies to an integral that is solvable. And here's the integral. Okay, minus cotangent theta minus theta plus c. Now, we're not done because we have to get the integral as a function of x, the original variable. And so it says this can be done either by using trigonometric identities to express cotangent theta in terms of sine theta is equal to x divided by 3. So yeah, every time when we use a trig substitution, when we're trying to get back to the x, the original variable, this is it's not as simple as a regular like a u substitution, because you had because of the way the new variable is expressed as a function of the original variable. So, but to get back, you're going to come to the substitution, right? So we had x is equal to 3 sine theta. You come back to the original definition of the substitution, and you're pretty much going to solve for the variable that you're trying to substitute for. So we're trying to get back to x, so we're going to solve for theta. And so you got sine theta is equal to, or it's x divided by 3. Okay. And now if you take the inverse of this, you get theta is equal to the inverse sine of x divided by 3. And that's what we're going to use to substitute for this theta here. But then for trig substitutions, what they do is, so the final answer for a trig substitution is either going to have just the variable you substituted for. So like here's just a theta, and so in that case you're just going to explicitly solve for theta in the original equation that you made, and replace the theta here. But then you also might have trig functions, and the trick that they use to like, okay, how are we going to replace the minus cotangent theta? What you do is, so again, you come to your original definition for your substitution, and here we get sine theta is equal to x divided by 3. And what they do is they make a right triangle with angle theta here, and they just make it positive. And then so sine of theta is opposite over hypotenuse, so they put x here and 3 here, and then use the Pythagorean theorem to get this side. And so with this triangle, it doesn't matter what, you can take any trigonometric function in the final answer and use this right triangle to replace the trig function. So tangent is opposite over adjacent, so cotangent is going to be adjacent over opposite. Cotangent is the square root of 9 minus x squared over x. That's how you replace cotangent theta. And then so here's the cotangent theta, and here's you have inverse sine of x divided by 3 plus c. Okay, now it notes, though, it says, although theta is greater than 0 in the diagram, so you might say, well, what about if theta is negative? This expression for cotangent theta is valid even when theta is less than 0. So you don't have to worry when doing this. You don't have to worry about, well, do I make the theta negative or positive? Just draw a right triangle with a positive theta, and then use whatever your original definition is for the substitution. You'll have that will allow you to put two sides of the triangle. It just depends if we had cosine theta, we could put this variable in this term and this term, or if the original definition was a tangent, I think we do tangent. Yeah, it's going to be a sine, a tangent, or a secant. So with a sine, you can put this side and this side. With a tangent, you can put this side and this side. And with a secant, that's 1 over cosine, you can put the adjacent and the hypotenuse. And then you just use the Pythagorean theorem to get whatever side you're missing. And then you can use that triangle to replace any trig function in the final answer. And then again, if you just have an explicit variable here that's not a trig function, then what you're going to do there is just solve explicitly for the variable that you substituted for. Then you can put the x back, get the x back in from there. All right, so there's a trig substitution problem. Okay, and just again to note, let's come to the end of this section, you can see all of these example problems. It shows it's in any integral that you've got like something, like a squared minus x squared inside of a square root within the integrand somewhere, right? All of these have that. I mean, there's some cases where it's like 9x squared minus 1, but you can still put this in that form, a squared minus, or x squared minus a squared in this case. Okay, now there are some cases where you've got like, here's a squared plus x squared to the 3/2. Here's x squared plus 1 squared. And so really the trig, what you can see based on this is that really the trig substitution is more about the a squared plus x squared or a squared minus x squared. If you have an a squared of something like that anywhere within an integral, and you feel like, okay, if I made a trig substitution that would be helpful to simplify this integral, then you can go ahead and use it. But for the most part, it's the trig substitution is really valuable when you've got some sort of square root, because with the trig substitution with the a squared minus x squared, what it gives you is like the trig function squared. So it's perfect. It eliminates the square root. That's why it's most commonly going to be the most valuable when it comes to like an even root. Okay. Find the area enclosed by the ellipse. So this entire area, and here's the equation for this ellipse. And so what we're going to do is, if we can get y as a function of x or x as a function of y, and then integrate with respect to x or y, then we can get this area. And so what they do is they just say, okay, well, let's get y as a function of x. So they solve for y, and you get y is equal to plus or minus b over a, square root of a squared minus x squared. Okay, but then they note that there's a symmetry to this, and that we can just, if we just integrate from for x is equal to 0 to x is equal to a, just using the positive form of this function, and then we can multiply that integral by 4 and get the area. Okay, so that's what they do here. 1/4 of the area is the definite integral from 0 to a of that positive form of that function. Okay, so we need to evaluate this integral, but how do we do it? And so we look at the integral, and we can't make a u substitution, but we see this a squared minus x squared. And in particular with the square root, which makes it, it's going to be even harder to deal with that square root, but not with a trig substitution. And so if we come here, here's the square root of a squared minus x squared. So we're going to use x is equal to a sine theta again. So dx is equal to a cosine theta d theta. And then they say that they update the limits of integration, which I would recommend you do if you're doing a substitution. And this is a little bit different than the u substitution but it's the same idea. What you do is you say, so we're going from the original definite integral is going from x is equal to 0 to x is equal to a. So what you do is you come to your formula. We said that x is equal to a sine theta, and you say when x is equal to 0, and then what is theta equal to? You have to solve for theta. Okay, then when x is equal to a sine theta, when x is equal to a, sine theta must be equal to 1. So theta must be pi over 2. Okay, and then they simplify this to a cosine theta. But you have to be careful, though, because if let's say you solved for theta for one of these limits of integration, and it went outside the minus pi over 2 to pi over 2 range, then you can't. This is defined only when theta is between minus pi over 2 and pi over 2. So you have to, you can't solve it at that moment. You'd have to make some changes. But we see we're going from theta is equal to 0 to theta is equal to pi over 2, so we're fine. All right, so then they solve the definite integral and get pi ab. And it just notes that we didn't have to worry about going back to the original x variable because it was a definite integral, and we updated the limits of integration based on the new variable. Okay, here's another integral, and you look at this and you realize you can't make a u substitution. If you said u is equal to x squared plus 4, then du is equal to 2x dx. That doesn't help you, but you see this square root of x squared plus 4. If we come back to the table, okay, square root of a squared plus x squared, this is x squared plus 4, right? You could just, this order doesn't matter. So we're going to say x is equal to a tangent theta with this domain restriction, and we're going to use this identity. So a is 2, x is equal to 2 tangent theta dx, and so it works out to where this square root of x squared plus 4 simplifies to 2 secant theta, okay? And then you're able to, it simplifies to, with that substitution, it simplifies to this. And now we can solve this using what we learned in the previous section, trigonometric integral techniques. And that's what they do, and they get, here's the final answer. And so, but we have cosecant theta. How do we got to bring this back in terms of x? And so what you do is you say, okay, x is equal to, the original definite substitution formula was x is equal to 2 tangent theta, and therefore tangent theta is equal to x divided by 2. Okay, so you can draw the triangle, put the theta, and tangent is opposite over adjacent, so you put x here and 2 here, and then use the Pythagorean theorem to get the other side, and now we can replace any trigonometric integral with the corresponding x expression. Okay, cosecant is 1 over sine. Okay, sine is opposite over hypotenuse, so it's going to be hypotenuse over opposite. Cosecant theta is square root of x squared plus 4 over x. They put the minus sign in front, and there you go. Okay, so here's just more standard examples. We're going to work a bunch of example problems. For this problem here, they note that you can do hyperbolic substitution. And you're welcome to pause the video and take a look here. This just works because of the hyperbolic functions have similar trig identities and derivative properties as regular trig functions. But if you come here, it talks about the hyperbolic substitutions can be used in place of trig substitutions, and sometimes they lead to simpler answers, but we usually use trig substitutions because trig identities are more familiar than hyperbolic identities. So, but it is an option if you want to use a hyperbolic substitution. All right, so let's take a look at example 6 here. We've got, in the integral, there's 4x squared plus 9 to the 3/2 power. So this is a square root, but really it's more about what do you do when you see something like this? It's kind of like a squared or x squared plus a squared, but not really. And so to do what you do here is you say, so okay, this is this is 2x squared, right? The 4x squared is you take 2x and you square all of 2x, and then this is 3 squared. And so what you're going to do is you're going to look at it this way. If you say u is equal to 2x, then you can write this as u squared plus 3 squared. That's 4x squared plus 9. Okay, so if we come back, u squared plus 3 squared would fall under this form. But if you treated u as, if you replaced u with x, right? And so in that case, we would say what? We have u squared plus 9. So that would be, we'd say the substitution would be that u is equal to 3 tangent theta, right? So we would say u is equal to 3 tangent theta. Okay, but u is equal to 2x, so 2x is equal to 3 tangent theta. Therefore, x is equal to 3/2 tangent theta. And so that's the substitution we need to make. So x is equal to 3/2 tangent theta, which gives dx is equal to 3/2 secant squared theta d theta. And if you make that substitution for x, you get the square root of 9 tangent squared theta plus 9. And then use the trig identity that the table gave us, and this comes to 3 secant theta. Okay, so with that, you can then solve the integral. Okay, now what about a problem like this? What you do here is you want to recognize if you've got something that you could perhaps turn into a sum or difference of squares. And so with this expression here, you can't turn it into an exact sum or difference of squares, but what you could, if you complete the square, then 3 minus 2x minus x squared becomes this, 4 minus x plus 1 squared. And so you can, if you say u is equal to x plus 1, then you've got 4 minus u squared. And then you could solve it that way. And so, if we come back here, like these are the base forms, right? These are the base forms where you can make a trig substitution. These are the only 3 base forms, but you still want to recognize offshoots from this. Okay, and so the first offshoot is that it might not always be a square root of the a squared plus or x squared or whatever. It might be like to the 3/2, or it might just be squared, you know. And then the other offshoots are if you can, you know, you've got something to where you can make a u substitution and turn an expression into that a squared plus or minus or x squared form, x squared minus plus or minus a squared form. Like we showed here, and then like here, right? Recognizing that you can turn this into something like this, and then this, you can make a substitution and get one of those trig substitution forms. Okay, so now let's work some example problems.